Okay, so this is a continuation of signal conditioning. So this video, what we are going to discuss is filters. Okay, so let me take my pen. Okay, right. Okay, so filters. So what's filters? Um, say you have a sensor. Okay, you have a sensor, and that sensor, okay, measures some physical quantity. Either it could be a displacement or velocity or acceleration or temperature, okay, whatever that signal. And the sensor senses that signal, and somehow it converts that into a voltage signal, okay. And the sensor senses whatever that physical quantity at each and every instant of time. So the voltage which it converts will also be a function of time. Okay, now when we somehow see the result of the sensor, what we will receive is not just the physical quantity, but also we will receive some noise. Okay, so this voltage will contain uh, the physical quantity. Let me call that as, let's say, P, okay, as a function of time, plus some noise, some error, okay, as a function of t. Okay, it's been combined. Okay, so for example, something is oscillating, okay, and I'm measuring the displacement of that, and the actual thing, the actual physical quantity behaves like this, okay, but the sensor, what it will give is, along with, I mean, addition to that, some noise, okay, some noise signal that has been added to this one. Okay, now I don't want these noise signal. How somehow I need to get rid of this particular noise signal, so that I will get only the voltage corresponding to the physical quantity. Okay, so how to achieve that? So that we can achieve through filters. Okay, um, the filters can be two types. One is digital filters. Okay, these digital filters work once you can somehow convert this analog signal into a digital form, and then you apply the digital filters using logic gates. Okay, but right now we are not gonna discuss about the digital filters. Let's say we don't have the luxury of converting the analog signal into a digital one, which means we need to rely on the analog circuit components, the components which just uses things like resistor, capacitor. Okay, if we make a circuit with resistor, capacitor, op amp, such things, then we call that as a analog circuit. And if we construct a filter using analog circuits, then we call that as an analog filter. Okay, so we are going to discuss mainly these analog filters. But before we discuss about the analog filters, I want to discuss something. I want to discuss something about the frequency, uh, the transformation between time domain and frequency domain. Let's say you have a signal. Okay, so this is time, and this is the signal, which is in the form of voltage. Okay, and you are getting some signal like this. Okay, what you will do is, normally these noises are in the having high frequency compared to the actual physical quantity. Okay, so what we do is somehow we convert this into a frequency domain. Okay, so whatever you have is in the time domain, and somehow you convert that into a frequency domain. Okay, uh, and then you say, for example, if these are the signals which are corresponding to the high frequency are the noise, then you just chop it. Okay, and you remove all these things, or you make these things zero. Okay, and then once again you convert that into a time domain. Okay, so that you will get smooth signal. Okay, so that's what I mean, that's one way of doing filtering. Okay, uh, but even before that, what I want you to teach is, what do we mean by converting the time domain into frequency domain and frequency domain into time domain. Okay, so basically what you will do is you will use Fourier transform. Okay, so which will do the conversion between time domain to frequency domain, and here it is inverse Fourier transform. Okay, so let's see, say you have a signal. Okay, the signal is sinusoidal. Okay, sinusoidal with some amplitude, let's say capital A. Okay, so basically the signal is uh, A sine omega t. Okay, so if that's the case, let's say this is the time period. Okay, this is the time period. Okay, and this cycle is being repeated again. Okay, and this is time. Okay, so the relation between this omega and t is equal to 1 by omega. Okay, so now if that's the case, mm, if I convert this signal into let me denote this as capital F of omega. Okay, then what's capital F of omega? If I convert this signal, okay, so this is the input signal which is represented like this in time domain. If I convert the same signal into a frequency domain, how does it look? Okay, it looks like a so at omega, so which is this omega. Okay, let's say that's this omega. Let me call this as omega 1. Okay, this is omega 1. Okay, at omega 1. Okay, and I will just draw a spike. Okay, and what is the height of a spike? The height of the spike is this amplitude A. Okay, and this is the conversion. So the Fourier transform of A sine omega 1t is just a spike at omega 1, and the height of that spike is A, which is the amplitude of the signal. Okay, if A is 1, then the height is 1, and if A is 3, then height is 3. Okay, by the way, this kind of signal where everywhere it's 0, only here it's A, right? Such a signal is known, or such a function is known as Dirac delta function. Okay, so maybe some other time we will discuss more about the Dirac delta function, but just now you just get to know the name of such function, which is known as Dirac delta function. Okay, now let's see some examples. uh, Say I have a function sine omega 1t plus sine omega 2t. Okay, if I convert this one into a frequency domain, okay, let's say a1 sine omega 1t and a2 sine omega 2t, and if you convert this one into a frequency domain, how does it look? It looks like a two spikes. Okay, one is at omega 1 and another one is at omega 2. Okay, so what's the height at omega 1? It's a1. Okay, let's say this is a1. Okay, and let's say this is a2. Then the spike over here is a2, and this is the transformation, okay, of this signal. Okay, say this is f of t, which is given like this. Okay, and this is the conversion of this time domain signal into a frequency domain signal. Say this is capital F of omega. Okay, and maybe we'll do one thing. We will open Desmos, and let's say sine t plus sine or 2 sine 3t. Okay, okay, I think here I should give it as a x. So y is equal to, okay, say for example, if I just draw y is equal to sine x, let me hide it for a while. So that's sine x, and another signal y is equal to 2 sine 3x. Okay, so this is y is equal to sine x, and this is y is equal to 2 sine 3x. And now if I add those two things, if I add these two things, okay, this is the signal I will get. Okay, this is the signal I will get. So if we has been given such a signal, this Fourier transform, okay, so let me rewrite those equation, that Fourier transform for the function which we are discussing is sine t plus 2 sine 3t, right? So that will be equal to, so the signal corresponding to this one, the frequency is 1, okay, maybe here it's 1, okay, and the height is, the amplitude is 1, okay, and then for this signal the frequency is 3, okay, so somewhere here 3, and the height is 2, okay, so that's the signal corresponding to where is it here? Corresponding to this signal, okay, maybe I will yeah, so corresponding to this signal. So this signal has been, if we convert this signal into a frequency domain, then this is what we will get. Okay, fine. So as an exercise, I will ask you this one. Let's say at 1 its the amplitude is 1. Okay, at 2 the amplitude is 1 by 2. At 3 the amplitude is 1 by 3, and it's keep on going. Let's say up to 10 the amplitude is 1 by 10. Okay, now that's given in the frequency domain, f of omega. Okay, what is the corresponding signal in the time domain? So if I plot it respect to time, this signal, okay, how does it look? Okay, so try that, and also try for different uh, such frequency domain values, and get familiar with the transfer between time domain to frequency domain and frequency domain to time domain. Okay, so with that we will conclude this lecture, and in the next lecture we'll see how to make use of this Fourier transform in filtering. Thank you.